So what we've done is we've drawn a diagram of our object. We have identified, at least in principle, all of the forces that could be acting on it. Two tensions, its weight, and some force here at the pivot point with unknown components. And now we have three equations that need to be satisfied for this to be in static equilibrium. So let's look at what the net force, I'm going to call this my first equation. What's the net force in the x direction? I know that it's going to be 0 because it's not accelerating in the x direction. And so what are those forces? Let's lay down a coordinate system for reference. X, y, positive upwards, positive to the right. Here's a force in the x direction. It's tension of the guy wire. I don't know what that is, but it's pulling in that direction, I'll assume. And nope, not weight, that's vertical. Not this tension, that's vertical. There must be another force here, because if that's going to equal 0, either that is 0 on its own, or it's being balanced by a force down here at the pivot, which certainly has a horizontal component, which I'll call force X. Now, I don't know what either of these forces are, but I do know they add up to 0, so they must be equal and opposite. So they're equal in magnitudes. That's what this little equation says. So from this one equation, I can tell that the tension in this wire is equal and opposite in opposite direction and equal in magnitude to the force at the bottom of this pivot. Otherwise, this whole thing, this whole boom, would be accelerating in one direction or the other. So I'm going to call this my equation 1. And it came from the horizontal forces, no horizontal net force. I'm going to call this little equation 1. All right, no net force in the vertical direction. What can I glean from that? Well, there is a tension in this wire here. I'm not sure why I called it L. Tension load. I'm just going to call it tension. There's a tension downwards. There's a weight downwards. Weight of the boom. Those two weights aren't necessarily the same. And then, well, both of those are pointing down. Notice there's two forces pulling the boom downwards. And it's not falling down, so something must be pushing it up. So the only vertical force left is this force at the pivot point. It must be pushing upwards. Again, I can bring these over and I can see that in total, the tension in this wire plus the weight of the boom itself is being supported at the pivot point. These forces are equal in magnitude, as shown here, and they're in opposite in direction. So this pivot must be supporting the weight of the boom and the tension in this wire. Now, I do know this weight, this tension. I do know this weight, so I can find Fy right now. Let's see what, and I'll call this my second equation. And what does the torque equation say? It says there's no net torque. And what are those torques? If I take this as my pivot point, these forces at the pivot point they just have a supportive effect. They have no twisting effect, because the lever arm for any force right coming towards or coming out of this pivot point. L is equal to 0 here, so there is no torque from any of these forces here, any component of this force. So I only need to think about the forces that have some lever arm, the effects there. So I'm going to think about the weight. Well, the weight is going to have an effect, but not all of the weight, only the perpendicular portion of it. This weight has two effects. And here we're going to have to be a little bit careful. With the diagram. This weight pulling down partially pulls the, well, I could do it up here. I mean, this is the same, it's the same triangle either way. If I put the vertical, I'll either draw a triangle here or I'll draw it there. So this weight partially is pulling this, is partially twisting this boom over. So perpendicular, there's a portion of the weight that is perpendicular to the boom, and then there's a portion of the weight that is parallel to the boom. I hope you can see that. And if you would have preferred, we could have drawn the components there if you would have liked. But so this weight here, the weight of the boom is partially pulling the boom towards the pivot point and is partially twisting the boom over. Now, I do know from the question, they've given me that this is 60 degrees. So there's my angle, and if this is 60 and that comes straight down, that's 90, this must be 30, so this must also be 60. So those two angles I know, and so the torque caused by the weight, the only torque caused by the weight is from this perpendicular component. So it's the weight perpendicular times the length, and the lever arm is equal to not the full length of the boom, but 0.385 of the length of the boom. And this is going to pull it in the counterclockwise direction, which, based on, for torques, this direction is negative and this clockwise direction is positive. So this is counterclockwise. Actually, no, wait a minute. I made this mistake in class too. Let's just be double careful. This is going to pull it this way. That is clockwise, and that is negative. So this direction is negative. This direction is positive. It's pulling it in a direction. So this is going to be a negative sign there. It's pulling clockwise, and clockwise is negative. Remembering that from geometry class, angles starting from the positive x-axis and sweeping upwards are considered positive. So this is our positive direction for torque, which is counterclockwise. Alright, I have a negative sign here, and the other torques are caused, I can come up with a geometrically identical argument for this tension here, in that this tension partially is perpendicular, partially is parallel, and with the exact same geometrical arguments, I'm going to say that it's going to have a very similar effect. Again, in the clockwise direction, so this is a negative, there's going to be a tension perpendicular, and it's going to be affected, it's twisting at the full length of the boom. And this force here has a, if I draw a line just parallel to the boom, and I draw a line perpendicular to the boom, I can see that this force here, which is the tension in the guy wire, is partially perpendicular to the boom and partially parallel to the boom. So this is the tension parallel. And there's my right angle. Always, all of these vectors, the source vector is the hypotenuse, and that's going to be pulling in the counterclockwise direction. So there's a positive value, and so this is tension perpendicular. This is for the guy wire, and it's also at the full length. I think I probably have to stop there.